Hey everyone, thank you for joining. This is session 2 of the NEAR web series presented by us and the Blockchain Acceleration Foundation and quite a few other university clubs. This session will be presented by the Cambridge Blockchain Society. We're a student club at Cambridge University, and yeah, we're very excited, and we've bootstrapped this in the last few days. So thank you to Dapp for all their ongoing support and the NEAR team. We have our guest speaker, Sebastien, as well from NEAR, who will be speaking at the end.
Right. To be clear, I do not work at NEAR. I'm the CTO of Dapp, but I'm close with them. Yeah, I do not work at NEAR proper.
Gotcha. You're still very knowledgeable at NEAR, so I'm personally looking forward to your section. Yeah, so I'm Taran. I'm a physics student at Cambridge. Imtiaz, Alex, and Mihal are computer scientists at Cambridge, and I think, yeah, Mihal's second year, I'm second year, Imtiaz and Alex are third year students. Yeah, let's get started. Okay. Yep, in this session, we'll go over what blockchains are. We'll go over briefly what the current implementations of different blockchains have been, and various mechanisms through which, I guess, consensus is achieved. And we'll also go over some cryptography bits behind blockchains, pros and cons of current blockchain technologies and the implementations, and finally an introduction to the NEAR blockchain given by Sebastien. Michal, kick it off.
All right, fantastic. It's great to be talking to you here. All right, so to kick off our introduction, let us first remind ourselves what a blockchain actually is. So, next slide, please. At the core of this amazing technology, we have a data structure. And this data structure is a timestamped append-only log. To unwrap that definition a little, timestamped simply means that all the blocks in the structure are chronologically ordered. Append only means that the only action allowed on this data structure, apart from, of course, reading the data, is appending a new block after the most recent one, which you can see nicely fits in with the chronological order and timestamping we have mentioned just a while ago. But at this point, any of you here could just come up to me and say, "But Michal, what is so special about this glorified linked list? Surely I could just go and change the data stored in this data structure whenever I want." And that someone would be right. Because by itself, this data structure is not yet what we would all agree to call a blockchain. So what else do we need? How can we ensure the immutability and enforce this chain to actually be append-only? The answer here is cryptography. And the two extremely important cryptographic primitives that are used to keep this industry up and running are hash functions and asymmetric cryptography. Hash functions provide us with tamper resistance and integrity, the backbone of the immutability that we seek here. The other thing we need here is asymmetric cryptography, to prove that all the transactions come with the consent of the entity that makes them. For example, it ensures that Adam will not be able to get any funds from Becky unless she explicitly agrees to it. And a bit later today, Alex will spend a little more time to go over the cryptography of blockchains more in depth. All right, so to quickly recap what we have here, we have a timestamped append-only log that is unfeasible to tamper with, and which ensures that no transactions are being made without consent. But there is still one more piece of the puzzle that we have not covered yet. Namely, if an entity is presented with multiple differing blockchains, for example, one with additional block appended and the other one without it, how does such entity decide which blockchain to assume to be the true one? And how can we ensure that all the participants in the network will be eventually converging on the same answer as to what the true state of the blockchain actually is? And for this, we need a consensus mechanism, which, for example, says that we always agree on the longest chain. And another big part of reaching agreement is Sybil resistance, and Taran will be talking about this later. So we now know what our blockchain is, but how do the blocks and chains actually look like? As Kevin showed us last week, it is pretty straightforward. The blocks consist of some data, which then hashes to a string of bits of fixed length. And then the links come from the fact that each block also refers to the hash of the previous block. Simple as that. Thanks to all of that, given our blockchain, we can ensure that it works in a decentralized manner by providing everyone with the ability of joining the network to receive and send updates to the state of the blockchain and to keep the current state stored on their private machine. All right, now we'll go over to Taran, who will tell you a bit more about the history and implementation of blockchain technology.
Thanks, Riha. Yes, so I'll give a brief history of blockchains and different mechanisms through which cyber attacks can be resisted. The first implementation, I guess a brief history of P2P content distribution. My favorite was BitTorrent. BitTorrent allowed a P2P data distribution network where different nodes in the network could seed data transfer over BitTorrent. And Bitcoin was the first implementation of a blockchain. I guess the blockchain usually refers to Bitcoin's blockchain. And Bitcoin was founded by Satoshi Nakamoto, who described Bitcoin as a purely peer-to-peer version of electronic cash, which would allow online payments to be sent directly from one party to the other without going through a financial institution. So what is consensus? In essence, blockchains are databases distributed to designed to record, communicate, and transact information without needing a centralized authority. Most blockchains are built on a network of distributed nodes, which are individual and independent, and they also work together to furnish the transactions that take place on the distributed network. Therefore, it is necessary for every blockchain network to have a mechanism that helps ensure all of its nodes are synchronized with one another and in agreement on which transactions are legitimate and should be agreed upon. This system is usually referred to as a consensus mechanism, but in reality, these mechanisms are cyber resistance mechanisms. I'd like to go over the Byzantine generals problem, which describes a kingdom trying to conquer another kingdom and has a lot of generals distributed around a city, and all of these generals have their own armies and have to make a unanimous decision. The decision could be whether to attack or whether to retreat. All generals need to reach consensus in order to execute in coordination, because if they do not reach consensus, you would end up with some generals attacking and some generals retreating, which is not efficient at all. When you apply this logic to blockchains, each general is a network node and the city is a blockchain, where each network node needs to agree upon the state of the blockchain in order to proceed and proceed with efficiency. To solve this, you have to solve the Byzantine fault tolerance, which is described by it is the dependability of a fault-tolerant computer system to such conditions where components may fail, and there is imperfect information on whether a component has failed. Blockchains need to build blockchains need to reach consensus in order to solve many problems. The first of which is the double spending problem. Say you have a record that says Alice has 100 bitcoins and transfers 100 bitcoins to Bob, which then leaves Alice with 0 bitcoins and Bob with 100 bitcoins. The double spending problem describes an attack where Alice somehow hacks the system and ends up in a state where Alice pays Bob 100 bitcoins and also pays Charlie 100 bitcoins. So it's described as a potential flaw in the cryptocurrency or other digital cash schemes, whereby the same digital token can be spent more than once, and this is possible because a digital token consists of a digital file that can be duplicated or falsified. What are cyber attacks? Cyber attacks are security threats on a system where an attacker tries to take over a network by pretending to be multiple users at the same time. Most blockchains need to prevent cyber attacks, and how do they do this? By making it very expensive to carry these out. There are different methods of reaching suitable levels of cyber resistance, which sort of target the attackers and make it very expensive for cyber attacks and make it very expensive for attackers to have multiple identities. First one is proof of work, which makes it very expensive through computation, where each miner has to solve mathematical puzzles, thereby using up energy, which costs money. and the prime example of this is the Bitcoin blockchain. Proof of stake, where each node and each miner has to have a stake in the blockchain. Usually with Ethereum, it's 32 ETH or more, and this makes it more expensive. Where if the miner is found to be lying, the stakes are slashed, and the miner loses his stake. There's also proof of authority. Proof of authority. Sorry, let me just bring up my notes. Proof of authority uses a reputation-based model where a centralized entity authorizes whether or not each node, a particular applicant for a node is accepted or not. This method is not decentralized at all, whereas proof of work and proof of stake are very decentralized and permissionless, whereas proof of authority is a permissioned way, is a permissioned resistance mechanism. Hand it over to Alex.
Yeah, thank you, Taran. And now let's talk about the cryptography used in blockchain in a bit more detail. So first, let's recap the hashes. As you remember, this has been talked about in detail in the last section, but just as a quick recap, a hash function is a mathematical function that, given a message, outputs some fixed length hexadecimal string. And it's important that it is quick to compute because we will be using it a lot in blockchain. And it has those properties where the output of this hash functions appears random, so that it is infeasible to forge an input to this function that would produce a certain output, and it's also infeasible to find the collision. So two messages that have the same hash value. And as has been said in the last section, such collisions will exist just because there's much more possible inputs than there is possible outputs. But because there are so many possible outputs in practice, the collisions will not happen. And if you can go back to for one more second, a good thought experiment that gives a lot of good intuitions about hash functions is if you imagine that you want to play rock, paper, scissors over the internet, and well, if you just say rock, then if you just give your move as plain text, then the opponent could just wait for you to give your move and then output a winning move, and you would have to somehow enforce that the moves are revealed at the same time. And instead, what you could do is have each player commit to their move by publishing the hash of the move, and then they would, after both of them have committed, they would reveal the actual move. And in this simple form, it has the problem that even though the hash function is pre-image resistant and so on, if there are only 3 possible inputs, the adversary can simply test all of them and see which one is the one that has been used. So it's so if you can guess the plain text that has been used to generate the hash function, the hash value, then you can actually break this property. So what you can do instead is append some randomness to your move. let's say 128 random bits, and then that will guarantee that no one is able to guess which move you have played or committed to. And then when you reveal your move, you also reveal this randomness and verify that it works out. So now we can go to Merkle trees. And Merkle tree is this data structure that allows us to compute hashes of many independent data points. So as you can see, to compute a hash of a set of values, we construct this tree where each node is a hash with 2 children. And this is used to, for example, compute a hash of all the transactions included in, for example, in a block of transactions in Bitcoin. And if we go to the next slide, we can see that in order to, for example, verify that some particular piece of data is contained in this Merkle tree, all we need to know, for example, to verify that that TB is in this set of data points, you just need to verify the hashes on the path from that data point to the root of the tree. So you just need to verify that hash of T is HB, and then hash of A and hash of B is H of AB, and so on to all the way to the root. And if we go to the next slide, we can see that actually you can think of the whole blockchain as a Merkle tree, because you have this Merkle tree as inside of each of the block, and also you have this hash of the previous block, and then you hash them together to construct the block header, to construct a block hash. So you effectively get this very unbalanced tree that has this property that you can quickly verify if data is contained in it, and so on. So that covers the hash part. And now a second very important primitive, as Michał said, is public key cryptography, which allows us to actually have identities on the blockchain. So in decentralized digital currency systems such as Bitcoin, users' identity is basically tied to their public and secret keys, and anyone can generate as many of those as they want, and so anyone can construct as many identities as they want, and that's what leads to this need for Sybil resistance that Taran talked about, that you cannot just say one person, one vote, because anyone can create as many identities as they want. And then the public key is essentially the address, and you can send, for example, Bitcoin to users' public key. And then in order to spend that Bitcoin stored under this public key, the user uses their private key to sign a transaction that spent that Bitcoin. And of course, we need this important property that it is impossible to compute the private key just from the public key. because if that would be possible, then anyone would be able to forge signatures. And so there are a couple implementations of this public key cryptography. One of them is so-called RSA, which uses the fact that it is mathematically hard to factor a product of two large prime numbers. So in this system, you start with two large prime numbers, and you use them to generate a public and private key, as you can see on line 6. And then this scheme can be used to encrypt messages, to send private messages from one user to another, but that's not really important for blockchains. What is important for blockchains is what you see on lines 15 to 17, which is basically using this RSA primitive to produce digital signatures. So when you want to publish a transaction that spends your Bitcoin, you'd need to produce a signature. So usually you first hash the message and then sign the hash of the message with the private key. And then when someone wants to verify your signature, they use your public key and do the computation on the signature and message hash. And yeah, that pretty much covers the cryptography used in blockchains such as Bitcoin. I will post a link into like the actual implementation of this RSA in the chat if anyone is interested. And now I'll hand over to Imitas.
Thanks a lot, Alex. Okay, so I'll talk to you guys about accounts, gas fees, and transactions, specifically using the Ethereum blockchain as an example. And in the next session, you'll get a lot more information about how all of this stuff works on Near. So let's start by asking the question, what is gas? Well, gas refers to the unit that measures the amount of computational effort required to execute specific operations on a blockchain network. Since each transaction requires computational resources to execute, each transaction requires a fee. Gas refers to the fee required to conduct a transaction successfully. Gas fees help keep the network secure, as well as providing node operators incentive to process transactions. By requiring a fee for every computation executed on the network, we prevent bad actors from spamming the network. And in order to avoid accidental or hostile infinite loops, in which a transaction or computation does not terminate and holds some portion of the network's compute resources hostage, each transaction is required to set a limit to how many computational steps of code execution it can use. The fundamental unit of computation is called gas. This also has the added effect of incentivizing developers to create more efficient applications on top of the blockchain, so as to minimize gas fees and in turn minimize the resources they use. Okay, let's take a look at how accounts work on a blockchain. An account is simply a mapping between an address and the associated account state, all stored on the blockchain's world state. Accounts store information about the account balance, a nonce, and potentially code and storage, depending on the account type. Account states are linked to addresses, which are generated through a hashing algorithm and used to verify transaction senders, similar to how Alex just told you guys about. All right, let's look at how transactions are processed then on a blockchain. Transactions are cryptographically signed instructions from accounts. An account will initiate a transaction to update the state of the network. A transaction refers to an action initiated by an externally owned account. In other words, an account managed by a human and not a contract. For example, if Bob sends Alice 1 token, Bob's account must be debited and Alice's account must be credited. This state-changing action takes place within a transaction. Transactions, which change the state of a blockchain, need to be broadcast to the whole network. Any node can broadcast a request for a transaction to be executed. After this happens, a node operator or miner will execute the transaction and propagate the resulting state change to the rest of the network. All right, so now that you guys hopefully have a good understanding of how blockchains work and what they are, let me tell you about why you should be using blockchains and why you should be interested in the technology in the first place. So let's go over the pros and cons of blockchains. Firstly, to understand and appreciate the pros of blockchain, let's take a look at some problems with our traditional implementations. When you deposit a check or receive a direct deposit in your bank account, you might expect the money to be accessible immediately, but that might not always be the case. There are a variety of reasons it may take several days for new funds to become available to withdraw or spend. It may take additional time for a check to go through check clearing. If the bank is out of state, the check may not be sent to the processing center until the next business day. The bank may have put a hold on your funds, or a bank mix-up may have taken place. Additionally, international bank transfers can take between 1 to 5 working days to be processed. So, how do blockchains address this? First of all, blockchain transactions are accurate. Transactions on the blockchain network are approved by a network of all computers hosting and validating the chain, thus removing almost all human involvement in the verification process, resulting in less human error and an accurate record of information. Blockchains also introduce some level of cost reductions, as typically consumers pay a bank to verify a transaction, a notary to sign a document, or a minister to perform a marriage. Blockchains eliminate the need for third-party verification, and with it, their associated costs. Blockchain transactions are also efficient. Transactions placed through a central authority can take up to a few days to settle, whereas financial institutions operate during business hours, usually only 5 days a week. A blockchain can process transactions 24/7, and they can be completed in as little as a few seconds, and can be considered secure after just a few hours. This is particularly useful for cross-border trades, which usually take much longer because of time zone issues, and the fact that all parties must confirm payment processing. Okay, let's move on to the next slide. So, blockchains are decentralized. This means they don't store any of their information in a central location. Instead, the blockchain is copied and spread across a network of computers. Whenever a new block is added to the blockchain, every computer on the network updates its blockchain to reflect the change. By spreading that information across the network, rather than storing it in one central database, blockchains become more difficult to tamper with, and the increased redundancy makes it more resilient to faults and attacks, as there is no singular point of failure. Blockchains are also transparent. Most blockchains are entirely open source software. This means that anyone and everyone can view its code, and it gives auditors the ability to review cryptocurrencies like Bitcoin for its security. This also means that there is no real authority on who controls the blockchain's code or how it is edited. Because of this, anyone can suggest changes or upgrades to the system. If a majority of the network users agree that the new version of the code with the upgrade is sound and worthwhile, then that feature can be implemented. Transactions on many blockchains are also transparent, and all the details of such transactions can be viewed and verified by anyone. All right, let's take a look at some of the cons of blockchains. First of all, one thing you might have all heard about, illegal activity. While confidentiality on the blockchain network protects users from hacks and preserves privacy to some extent, it also allows for illegal trading and activity on the blockchain network. The most cited example of a blockchain being used for illicit transactions is probably the Silk Road, an online dark web, illegal drug and money laundering marketplace operating from February 2011 until October 2013, when it was shut down by the FBI. However, illicit activities like cybercrime, money laundering, and terrorist financing made up only 0.15% of all crypto transactions conducted in 2021, according to a report from Chainalysis, a blockchain data platform, showing that the growth rate of legitimate activity far outpaced the growth rate for illicit activity on the blockchain. Next slide, please. So, technology costs. You've also heard of this one for sure. Although blockchains can save users money on transaction fees, the technology is far from free. For example, the proof-of-work system, which Bitcoin uses to validate transactions, consumes vast amounts of computational power. In the real world, the power from the millions of computers on the blockchain on the Bitcoin network is close to what Czechia and Austria consume annually. Steps are being taken to address this issue. Many newer blockchains utilize proof of stake to validate their network, and large blockchain networks such as Ethereum are also moving away from proof of work to proof of stake, greatly reducing their energy usage by up to 99%. Blockchains also have some level of speed and data inefficiency. Bitcoin is a perfect case study for the possible inefficiencies of blockchains. Bitcoin's proof of work system takes about 10 minutes to add a new block to the blockchain. It's estimated that the blockchain network can only manage about 7 transactions per second. Although other blockchain networks such as Ethereum perform better than Bitcoin, they are still limited by the time it takes for blockchains to reach a consensus about a new block between all the nodes. Whereas legacy brands like Visa can process 65,000 transactions per second. Solutions to this issue have been in development for years. There are currently blockchains that are processing more than 30,000 transactions per second, and many scaling solutions for existing blockchains that are being developed and deployed, such as sharding and zero-knowledge proofs and other layer 2 scaling solutions. The other issue is that each block can only hold so much data. The block size debate has been and continues to be one of the most pressing issues for the scalability of blockchains going forward. All right, great. So now that you guys understand what blockchains are about and the current issues and benefits to using blockchains, I'll pass it on to our guest speaker, Sebastien, who'll tell you more about the near blockchain.
Yeah. Hello, everybody. So today I'm not going to be diving into the specifics of the near blockchain and how it's fast and whatever. What I am going to be doing is doing an introduction to the near blockchain as to what problems it solves and why we love it here. So a big problem with existing blockchains is, yes, scalability. People talk about it a lot. You know, Imchaz just said that there's only 7 transactions per second on Bitcoin and Ethereum does around 12. So that is going to be a big problem for mass adoption, but that also begs the question, well, do we even have mass adoption yet? How do we get that sort of transaction volume? There just are so few people using it that does it even make sense to build a blockchain capable of 50,000 transactions per second if there are so few users? And the founder of Near actually put this quite aptly in this quote that I'll give you guys a moment to read and let that sink in. Cool. So basically, we kind of had this question is, okay, so why are there so few users? Why are there so few people using blockchain apps? Well, the reason for that is just because they're really hard to use. In order to use an application, at least on Ethereum, users have to pretty much do the following before they can do anything. They have to register for an exchange. They have to submit their KYC, which is like, you know, submit your passport or identification, and then maybe wait anywhere from a few hours to several days. It also means, right, so like, because then the exchange then has to sort of approve your account by checking your identity. They'll go to the government, they'll say, hey, they'll do a background check, whatever. That takes time. Then they need to buy some ETH, right? So they need to pay before they can even try the app. Then they need to install a browser plugin. Then they need to open the browser plugin and take their seed phrase. They need to basically write down their seed phrase, find somewhere safe to store it. Then they need to echo it back into MetaMask. Then they need to do is go to the exchange, transfer their ETH back to MetaMask, and only then can you finally open the app. And when you open the app, you'll see that when you press the button, you have to pay like $30 in gas just to like buy a kitty. Not just like if you want to buy a crypto kitty, you know, the crypto kitty might cost $5, but you still have to pay $30 in gas, right? And then you're waiting for like many minutes. So this is like a big problem because this basically results in maybe like a 99.9% drop-off rate where someone is interested in using an application, but they don't end up doing that because who's going to do that? Sure as hell, my grandma is not going to do that. Nor are my parents, and nor are most of my friends. So how does Near sort of address this? So there's 2 things. One, it has to address the wallet experience of getting set up. Because if you notice that setup process has less to do with the actual applications and more to do with the wallets. Two is by making the transactions cheap. So, so let's go to the next slide. Cool. So on Near, the way they solve this is all accounts are smart contracts. Now, what does this mean? So what does this mean? Let's start with like how identity works on other blockchains. On other blockchains, your public key is your address. Sometimes it's a hash of your address and some other function of your, a hash of your public key or some other function of your public key, but they're tightly coupled. Every account has one public key and every public key is one account. So the way a wallet typically works is, the app will sort of build a transaction and then it'll ask your wallet to sign it. And then the wallet will say, do you want to sign the transaction? Do you approve? And if you say no, then the app is sad and it can't send your transaction and steal all of your money. If it says yes, then it'll sign it. Now that the transaction has a signature, it'll give it back to the app and the app will send it to the blockchain. Next slide. Can we go to, Tarang, can we go to the next slide? Cool. Wait, should I go back one? Cool, yeah. So now on Near, we actually do this differently. Instead, every account has a smart contract proxy. And what this means is now there's a smart contract, a program on chain that sort of can maintain an access control list of public keys that are allowed to sign for your account. And that means that you can do a few things. And what this looks like is we've just sort of modified the flow chart, but now there's an extra step where instead of the app sending it directly to the application that lives on chain, they're sending it to your smart contract proxy first. And that proxy can use whatever logic it wants to decide whether or not that transaction should be forwarded. And this is cool because now we don't have to have a one-to-one correspondence between public keys and accounts. You can have, for instance, go to the next slide. So you could do is, for instance, in your smart contract account, you could have a list of access keys where every access key is for a specific device. So for instance, let's say I wanted to have access to the same account on my laptop, on my phone, and maybe on some other device. I now don't have to have separate keys, and I don't have to take my seed phrase and put it into all of the devices. All the devices can have different keys, but still access the same account. And also, if my device gets stolen, I can go in later and revoke access to the key that was on that device. So then I don't lose anything. We can also implement, go back, yeah. You can also implement application-specific access keys, where if I have a key that's only for one application, so let's say there's like one token, I have a key for that token, I have a key for another token, I have a key for another token. And so if an attacker managed to steal one of my keys, they can't take all of my assets. So this is really good for security. You can also implement the sort of opt-out custody where applications can implement a sign-in with Google user experience that's very easy to use. But the cool thing is that at any time, the user can revoke access to the sign-in with Google key. So they can sort of like exit custody whenever they want, which is very important for onboarding users because most users are like entering in your password. Doing a username and password is now like a lot of work. Why would I do that when I can just click sign in with Google? And that's what people are used to. And so we can actually reduce the friction to onboard, but then we can also say that, this is not secure. And once you have, say, if you have like $10,000 in there, you shouldn't rely on Google for that. And so what you can do is generate new keys, do the wallet setup, and exit later. You can also rotate keys. You can recover keys, and you can do a lot of other things that make it much easier to build user experiences that eliminate that really complicated and long onboarding step. like like for instance, you can write the smart contract wallet to pay for the user's gas. So then actually user doesn't need to own Near before they use an application. This is another cool thing that you can do. So this, like scalability, sharding, which we'll talk about soon, is all cool. And that's probably the thing you've heard about. This is the cool part, because when push comes to shove, who cares if your if your blockchain supports 20,000 transactions a second, if there's only say 500 transactions per second worth of users. Cool. Now, finally, next slide. Sorry about that. Now, before we talk about sharding, does anybody have any like questions about the account, the smart contract account model? No? Okay. So the way now, so now the way the network handles the cost problem is sharding. Now, consensus is ultimately limited by the network. And what I mean by that is when you're doing consensus, you have lots of computers located around the world, right? And so when you're doing consensus, you basically, all of these nodes have to send a lot of messages all around the world to reach agreement on the consensus of one block at a time. And you can't do consensus for multiple blocks at the same time. It's one at a time. So this is why if you have a single linear blockchain, you're ultimately limited by how much bandwidth, how many messages you can send around the world. With sharding, what we can actually do is split it up into little blockchains that each individually consume smaller bandwidth. And then we just need a way to link all the little blockchains together. And so if you've ever heard the word concurrency or parallelism, that's what this does, is it allows you to sort of scale by doing multiple consensuses in parallel and then linking them together. Next slide. Problem with this is that it's really hard. And it turns out this is actually a very complicated problem to solve. Now, the reason why it's hard is because if you have a single blockchain, if you want to carry out the sort of 50% attack, which is like on Bitcoin, if you had 51% of if the hash power of the hash rate, you can take over the network. But with Bitcoin, like getting 51% of the hash power is nigh impossible. So that's why it's secure. Now, if you were to break that blockchain into 10 little blockchains, now, in order to publish invalid transactions, you actually only need to corrupt 10% of those nodes. So now you only need, instead of 51%, 5.1% of the nodes. Now that's an attack that's actually quite feasible. So sharding is actually really hard because what you're doing is when you split the chains, you're also splitting the security. And I'm not going to go into the details of this here because it's actually very technical, very complicated, and there's a lot of steps to making it work. But Near is unique in that they're like one of the only blockchains in production that has actually solved this problem and like crossed their I's and dotted their T's and supported all the things that you need to support. And so if you want to read more about that, I put a source in the bottom right to the Near sharding paper. So if you're a technical person, you can read that, and that'll if you're curious about learning about the specifics of how the sharding works, you can read that. But this is like a whole other talk in and of itself. But yeah, so that's all I have. So the two things that make Near so awesome is the account model and sharding. Does anybody? But otherwise, that's it. If the chain is using sharded, the gas fee will be a lot. No, it won't be a lot more expensive. The gas fee will be, so you can think of like gas fee price as so the gas price is sort of like a supply and demand thing, right? So if you can support more throughput in the network, let's say like the network supports 200,000 transactions, that's like the supply. And the demand, let's say, is like 1,000 transactions. Well, then it's gonna be cheap. Now you look at Ethereum, where Ethereum supports 12 transactions a second, and maybe there's a demand of like 500. Then the transactions are expensive. Does that kind of make sense? It's just a supply demand thing. Does that answer your question, Carice? Of course. What do I think about the blockchain trilemma? It's a buzzword, And it's an oversimplification that sort of like gets away from the details. The devil with this stuff is always in the details. You know, it's not just like, oh, sharding is a drop-in solution for X or Y. You can, as long as you solve all of the problems in your specific domain, I don't think the blockchain trilemma is actually a helpful mental model. I think the blockchain trilemma, when it was created, it wasn't supposed to be this is like something that's unsolvable, or this is something that is like impossible, or like this is like an axis where your solution will always fall. The blockchain trilemma was sort of just like a way for them to describe the nature of like the blockchain, where this guy named Vlad Zamfir said, oh, look at these other blockchains now coming up. And they seem to fall somewhere on this triangle. But it wasn't him saying, but by saying that, he didn't say that all blockchains would fall on that triangle. Does that sort of make sense? It's like him like expressing a trend more than a hard and fast like law or rule of existence. So I think the blockchain trilemma isn't something to think about as like, oh, transcending it or whatever, or like a fact of life that you can never solve it. I don't think that's true. All right, Katya says, is it correct that near shards are split as Aurora currently operates on one shard and the rest of transactions on 3 other shards? I am not sure about the specifics. Now, one of the things about near sharding is that the sharding is very flexible, so they can do things like that. And I would not be that seems like a sensible split for them. And then the follow-up is near able to add more shards dynamically now? I am not sure. I don't think that's a thing that's released yet, but it's something that they are working on. And the cool thing is, of course, like the dynamic sharding is like, yes, it can support big increases in demand, which is something other blockchains have historically struggled a lot to deal with. Can you explain Rainbow Bridge? Okay, let me respond to Troy's follow-up before I answer this. So you think technical progress can give scalability and throughput with no sacrifice in things like security? Yes, I do think so. I just think that it's just like the technological progress is in the details. And Near did it in like the sharding and like some things with that. Now of course there's no such thing as a free lunch, so there are trade-offs with Near's approach, one of which is cross contract calls. So if you want to have a smart contract call another smart contract, it actually resolves sort of asynchronously. So the first contract call might happen in a different block from the other contract call. So that is a drawback that sort of adds some complexity to the developer experience. So there are still trade-offs, but things like zero knowledge proofs or roll-ups or other things, they can in principle give scalability without sacrifice in security. And that's just because what they're doing is they're not doing consensus. It's like, why should we agree on things when I can just prove it to you? Because agreeing is expensive. Proving is now getting easier. Okay, Rainbow Bridge. So I don't have a very deep technical knowledge of Rainbow Bridge, but my understanding of how it works is that it takes a piece of data on Ethereum. So if you remember, Alexander talked about Merkle trees. So everything on Ethereum is in a Merkle tree. And so what it does is it pulls the data, but also the Merkle tree proof from Ethereum, and then it puts it on Near. And then a smart contract on Near can verify the Merkle tree proof so that they can say it in fact was on Ethereum. That's like the high level of how it and other bridges work. Is it possible to scale one Dapp on many shards? For example, if Aurora requires more than one shard of, yes. So in fact, the details, if you read the paper, the details of the sharding is actually kind of cool, where it's not that applications ever live in one shard. The data is actually sort of split into like shreds, and then they're sort of like randomly split across the shards. So every application kind of lives in every shard. So if you want to split to more shards, you always can. Alexander, what would be the advantage of using? What would be the advantage of using Dapps existing on multiple shards? So if you're on multiple shards, basically it can scale more. So let's say like you build decentralized Twitter and everybody's using it. one shard might not be able to support it. And so you can put it on multiple shards. But the cool thing about Near is that the developer doesn't even have to think about it. Like the system just automatically does that. Yeah, of course, Troy. Alexander says, okay. Reek says, can you briefly expand Merkle tree? Alex, do you want to do this, or would you prefer me to do this, or who?
Yeah, do you mean Merkle tree as in?
Yeah, like the thing you talked about. I think they have some questions about it. If you would like if you want me to talk about it, I'm happy to, and you can also revisit it. Do we have the slides up? I can also share my.
Maybe you can give some other angle than what I have been able to.
Okay, sure. Yeah, I can totally do that. Let me share. Or no, wait. Okay, cool. Everybody see this?
Yep.
Okay, cool. Awesome. So the Merkle trees generally fall under a category of, this is a here someday called that.
Sebastian, you're lagging quite a bit.
But instead of A, B, let's think of them as just an array of values. You have T0, T1, T2, T3, T4, T5, T6, and T7. And yeah. Now, what we can do, you can't hear anything. Uh-oh.
You're lagging quite a bit.
Is that on my end?
Yeah, I'll share my
hear me
screen.
all right?
I'll share my screen, Sebastian. I think it's the internet connection on your end.
Okay, can you hear me all right now?
Yeah, much better. Oh wait,
okay,
try
cool.
that. Yeah.
Awesome. Yeah. Katya, can you hear me all right now? Awesome. Yeah. Sorry about that. Anyways, we're saying, so imagine like all your T's, you have this array. What I want to do is I want to sort of commit to that array. Right. So when I put it in a block, I want to make sure it never changes in the future. That even if you don't trust me, I can't change it. And if I did, or more specifically, if I did change it, you'd be able to know. So the way I do this is I actually interpret this array of elements. It doesn't have to be a transaction. It could just be data as the leaves of a binary tree. And the idea, and H is hash, correct. So HA is the hash of element A, and HB is the hash of element B, and so forth. And then what we can do is have HAB be the hash of A and B. So we take the two hashes and we hash them together and we get a new hash. And so at the next level, so we had 8 hashes here. The next layer, we have 4 hashes. You can do the same process again, and now we have 2 hashes. And now we only have 1 hash. Sorry. And so what this allows a blockchain to do, or really anybody to do, is I can commit to a large number of values with just a single value, which is the root hash. Okay, does that at least make sense? So what I'm doing is I give you a value, I give you this root hash, and that's saying, Tiffany says, yes, that is correct. So the hash AB is what it doesn't necessarily, no, hash AB is, you can think of it as like a function. So let me write this out in chat if this might be helpful. So we have HA, so HA is equal to H of TA. And then we have like HB is equal to H of TB. And then we have HAB is equal to H of HA appended. So I'm going to use some notation that you'll probably see elsewhere. So this double pipe thing, like the 2 lines, that means append. So if HA is a string, I'm just appending HB to the string. So it's HA, then HB, and I stick it into a hash function. Right? So what HAB is, it's a hash of 2 hashes. Does that kind of make sense, Tiffany? So it's not that it actually contains the transaction, it's a hash of the previous hashes. And because I can't invert the hash, I can't have made up this hash if I didn't put in the transactions originally. So, right. Okay, so there's 2 steps to this, right? there's first what we call the commit phase, where I have the array, and what I do is I build the hashes up the tree. So when I'm building the tree, I go up. Does that make sense? So what I end up with is, yes, correct. So what I end up with is a tree that I can just, so after I build the tree, I can publish, say, to the world, maybe on a billboard, or I can just like send it to you, the root hash, the root element, which is just a hash. And what this does is this is a commitment to all of the elements, right? Now, this is useless until we get to the second step, which is the reveal stage, stage, or also sometimes called the opening stage, where let's say, so I gave you that hash, I built the tree. Let's say that was at block 5. Let's say at block 10, you want to know that your transaction was included in block 5, right? Well, you already have the hash of block 5, so you know the root of the tree. So then what I can do is I can send you, and you want to know, and so I can send you your transaction, which let's say it's transaction B. Then I can also send you HA, HCD, and HEFG. Okay, and you already have the root hash. Then if you want to know that I am not, I'm not bullcrapping you, I'm not feeding you lies, I'm not lying to you, you can take TB, you can calculate HB yourself, then you can calculate HAB yourself because I gave you HA. And then I can also calculate, then you can also calculate HABCD yourself because I gave you HCD. And then you can also calculate the root yourself because I also gave you HEFG. And then you check that if the root you just calculated is the same as the one I gave you 5 blocks ago. If that is the case, then you can conclude. Okay, so like basically what I'm saying is like the verification step is like you can do that at any time after. So like imagine this tree is like all of the transactions in block 5. Then like if you say, let's say you submit your transactions and you waited like an hour and you wanted to come back and make sure you know that your transaction was in block 5. So you have the hash, the root hash. And so what you can do is then verify up the tree.
Yeah, I think it will be clear if you show the next slide.
What, this?
Yeah.
Yeah. So like in practice, what this means is like if you have, thank you. Yeah. So in practice, what this means is like if you have in a blockchain, you basically the Merkle root. So when we say the Merkle root, that means this root hash, this HABCDEFG. And that goes inside the block. And so since the block is like sort of published everywhere, everybody knows the Merkle root. And then at any point in time, you can ask a node, even if you don't trust it, you can say, hey, is my transaction in the block? And then they can prove it to you with the hashes. Yes, Near uses a similar Merkle tree process. Every blockchain, so this Merkle tree is like sort of like binary Merkle tree. And Bitcoin uses a binary Merkle tree. Ethereum uses a slightly different Merkle tree. So they actually use something called a trie or a prefix tree. This is like starting to get into like the weeds of like the CS, but it's the same process, but just with a different kind of tree. Near also uses a kind of trie, but it's not the same as Ethereum's trie. And Solana has a similar process, but it isn't a tree. It's like, it has a similar process, but it's different. Yeah.
Wait, is the trie used to actually include transactions in the block? I thought it's only used for to keep track of the state.
It's used for 3 things. So there's a transaction trie, there's a state trie, and there is a receipt trie. So there's 3 tries and they're all tries.
Right.
So here, so we can think of it in 2 ways, right? So this is like maybe a little bit confusing. So easier way to think about it. So Sungwoo, it's a good question. Every tree has, you can think of it as like every block is its own tree. And then the idea is like, if I have the block hash, so the block hash includes a hash of the Merkle root, includes the Merkle root hash. And then also the previous hash, which includes the Merkle root hash. So if I give you the block hash, I'm still committing to both trees, but every block has its own tree. Yeah. And the reason for this, there's a lot of different reasons for this, and this gets into the nitty gritty of like updating a Merkle tree, because the issue is like, if you want to insert an element into a Merkle tree, right? So let's say I wanted to insert an element, say, I don't know, TI, that's like over on the right. What I would have to do is I'd have to sort of create more nodes and update the hashes. And then I might actually need to add another layer to the tree and make the root hash that new layer. So, and that can be slow, because that's a lot of hashing, that's a lot of lookups, that's a lot of whatever. And so they usually like to batch this by block, and just every block has its own tree. That's what they usually do.
I think.
Yeah, of course. And
yeah.
what is this? Okay, I'm sorry. Let me stop sharing my screen. Does
Yeah,
anyone else have any
thanks.
other like questions about these?
Also quite conscious about time.
Yeah. Let me also give a thing about Merkle trees. There is a really helpful visualization that is really good, that I highly say, like, if you're just trying to get a better feel for like sort of grok how the trees work, check this out. This is like, somebody was nice enough to make like a little web app where you can sort of like, so you can click on a node and you can like update the value, and then you can see how the hashes change. And then if you hover over a value, it'll show you what hashes need to be given to prove. Yeah, this is a good thing to play with, to like learn about it. Yeah, of course. I don't know if we have, I know it's like maybe a little bit over time, but I'm happy to keep answering your questions.
Yeah, I've got to hop off. Thanks, guys, for presenting, and thanks everyone for attending. There'll be a workshop, session 3 this time next week. Hope to see many of you there. Bye for now.
Of course. Yeah, and be sure to like, follow BAF, join us. We've got, if you want to meet cool people at other universities who are doing this sort of thing, definitely come and join BAF.